All right, stat 1150. What I've found on the central limit theorem is it seems like this is one of the tougher concepts for my students to learn. But when it really gets kind of crazy is when we throw these types of problems all together. So look at central limit theorem for means and proportions and combine it with what we talked about in just the normal model videos. So what I like to do is I like to do at least one handout, this one, where we throw everything together. And this is going to simulate a lot more closely what your final exam is going to look like, because your final exam won't just say, okay, here's a central limit theorem for proportion problem, and here's one for the mean problem. They'll just be intertwined into all the different types of problems that you will be seeing on your final exam. So I feel like the bearer of bad news, but that's just the way it'll happen. Okay, guys, let's do it. This is again uploaded to the folder handouts on Blackboard. So when I read this problem, it says the duration of human pregnancies is normally distributed with a mean of 266 and a standard deviation of 15. I know right off the bat, because of the keyword mean and standard deviation, that this is a problem that addresses either the normal model and or the central limit theorem for means. Okay, so what is the probability that a woman, so when I see that, I think n equal 1, so one woman is selected at random and has a pregnancy that lasts between 250 and 262 days. Now I'll tell you what I want to do. I want to just split screen here. And then I've got stat crunch. Let me get it exit full screen. All right, so what I want to do to work this problem is just like before, go stat calculator and go to normal. And since I want between, I'm going to hit the between button, and I have a mean of 266, standard deviation 16, and I went between 250 and 262. And I'm done. So we don't have any standard error here. We don't have anything that deals with the central limit theorem for means, because even though it says we're talking about a mean, the reason is because we're taking a sample size one at a time. So we don't get any to the central limit theorem until we get sample size of 2 or bigger. So the answer here would be 0.2426. What length of pregnancy represents the 82nd percentile? Well, the 82nd percentile is the pregnancy that has 0.82 of the area below it. So I need to go to standard. So I need okay, hold on just a second. Sorry about that. I thought someone was knocking on my door. So I want the area below, because it's the 82nd percentile, to be 0.82, and then I'll go compute the value. So 281 days. It's just on the boat yesterday with my family. We were out with another family, and she is pregnant. And this actually came up, believe it or not. Do you know that the mean gestation period is 266 days? She didn't care. She knows her due date, and that's all she cares about. A certain obstetrician is currently providing prenatal care to 12. Now, guys, when you see that, you should need to think central limit theorem, because we're taking it more than one at a time. So according to the central limit theorem, what are the mean and the standard error of the distribution of sample means? Well, guys, remember the mean of the distribution of sample mean is equal to the mean of the population, which in this case is 266 days, and the standard error, or the standard deviation of the distribution of sample means, is sigma over the square root of n, which in this case is 16 over the square root of 12. And we can put that in our calculator if we enjoy doing stuff like that. Which, yeah, whatever, we will. So 4.62, yeah, days. All right, what is the probability that the mean duration of these patients, so these 12 patients, will be less than 270? So I have to do the same thing, except I have to come here and divide by the square root of 12. And you have no idea over the many, many years I've taught this, and I've taught this class over 100 times, how many points I've taken off because people get sloppy and they don't divide by the square root of the sample size. So guys, don't do that. Don't miss a problem that you know how to do just because you get careless. So 0.8068. All right. Second problem. A waiter who typically waits on 25 tables over a weekend of work believes that the distribution of his tips has a model that's positively skewed, which you would expect with tips because it deals with money, of $12 and a standard deviation of $3. Estimate the probability that he will earn at least $325. Well, if he earns $325 over 25, was it 25 tables? Then his average per table is $13. So we have to get it in this unit because the parameter that we're talking about is per table. So we need to get the average per table. So at least means what? More. So earn more than $325. So this is an easy problem, guys. The mean is 12. The standard deviation is 3 divided by the square root of 25. It's a good thing it wasn't 24 because, guys, we could have a sample size of 25 or more before we could use the central limit theorem. So we want greater than the average of 13. So not a very good chance. .0478 if I rounded correctly, which I think I did. So he's only got about a 5% chance of making this much money, and really it's only $1 more, but it's just not likely he's going to do that. How much does he earn on the best 10% of all weekends? Well, then what we need to do here is we need to come in and do below, set our below level at 0.90, or if you want to look at it this way, we do our above level at 0.10 and compute. So $12.77 per table times 25 tables so he earns $319.25 on his best 10% of all weekends. So that's the minimum amount to be in the top 10%, $319. So for him to make $325 would be rare. To make $319 would kind of be rare, be in the top 10%. Next problem: nearly all Americans report that they brush their teeth daily. Well, I find comfort in that. However, only 12% of Americans report that they floss daily. All right, that's surprising to me. Now, what I want you to know here is we're moving into a different type of problem. Up here, this one was easily identified because it talked about the mean of 266. When you see your value that describes your population, and in this case it's all Americans, how much they floss daily. I'm about ready to sneeze, so hold on. Oh gosh. When you see that as a percentage, then you know you have proportion problem. And proportion problems are linked to categorical data. Why? Well, why is this categorical? Because when a survey or however this information was collected, when they ask if they floss, the answer is either yes or no. So it's categorical, yes or no, making it a proportion type of problem. And that's really complicated for students, and it's the reason I haven't focused on it just yet, is because when you look at 12%, you're like, Dr. Darber, that's a number. That's quantitative. You're right. But these quantities and percentages represent a count in categorical data. What percentage of cars are Chevrolet? Well, that's categorical because it's either Chevrolet or not Chevrolet. So keep that in mind. A random sample of 1,000 Americans is selected. What is the probability that at least, guys, remember at least, again, is more than 13.5% will report that they floss daily? So guys, let's go over here. The mean of the distribution is the 0.12. The standard deviation is the square root of 0.12 times 0.88. And guys, where's the 0.88 come from? It's 1 minus 0.12. It's been discussed in previous videos. And we have 1,000. And then we close it up with the parentheses. So we want more than 0.135 and compute. So the answer is 0.0722. All right, second page. A random sample of 1,000 Americans is selected. What's the probability that that's the same problem? We don't need to do that problem twice. Now, this is something new. A random sample of 500 Americans is selected at random. 63 report they floss daily. Calculate and interpret the z-score. Guys, the z-score that we've looked at before has been like this. But when we get into proportions, it takes on a new look. And what happens is, if we think about this, this is what we collect from our samples. So we know that if we're calculating a z-score for proportions, that the sample notation has to take the place of this. We know that the mean of the sampling distribution for proportions is just p. And we know that standard deviation doesn't apply to sampling distributions for the proportion. Standard error does. And we should know by now that it looks like this. So our p hat is what we get from our sample. So that's 63 out of 500. .126. The p on the other side, we just did that. The p was what? 0.12. And the standard error is 0.12 times 0.88 over our sample size here is 500. Now, if we can put that in our calculator without doing something insane, we're going to be good. So, guys, I'm going to put the numerator in. So as I tell you, don't do anything insane. What did I do? I did something insane. Put the numerator in parentheses, and I'm going to divide by the square root. 0.12 times 0.88 divided by 500. And I get a z-score of 0.41. Now what's important, and I want you to know, is that because our p-hat was bigger than our population proportion, then our z-score had to be positive. If this had been less than, then our z-score, of course, would have been negative. Guys, I'm going to skip this one. I no longer cover that. It's going to come up in our next topic in confidence intervals, and I think I'm going to leave it to present it in that context only. Number 4, the mean and standard deviation of ACT scores in a particular year was 20.4 and 4.8. So the mean is 20.4 and the standard deviation is 4.8. 200 students are selected at random, then find the estimated probability that their average ACT is less than 19. Guys, this is an easy problem. 20.4. Standard deviation is the standard error, so we've got 4.8 divided by the square root of our sample size, which is 200. And we went less than 19. Very, very, very rare. Only how many zeros are there? 5? No, 4. So it would be very rare to have 200 students that has a ACT of less than 19. Number 5, I'll tell you what, I want to go down to number 6 first, and then I want to come back to number 5, and I want to put full screen on for it. House prices in a large city are positively skewed with mean 85,000, standard deviation 2,800. What's the estimated probability that a randomly selected price in this city, or I should say randomly selected house, in this city has a price that is above 100,000? Well, guys, you cannot do this problem. And some students will say, well, heck, I can't. I can come right over here and I can put in 85,000, and I can come over here and I can put in 2,800, and I can push buttons having no idea what I'm doing. So what are we talking about? Price above 100,000? And compute it? And you say, well, I got my answer. Well, no, you didn't. The thing that you're missing is right up here when it says normal calculator. That means you got to have a normal distribution. This doesn't have a normal distribution. It has a positively skewed distribution. And when I say what is the estimated that a randomly selected house, I'm saying n equal 1, so the central limit theorem does not apply. Unlike the problem over here with the waiter that we had. Where was the waiter? Oh, here's the waiter. Unlike the one with the waiter, see, we had a sample size of 25 or bigger. So the central limit theorem kicks in, making the distribution of sample means be a normal distribution, so we can use that over there. But when we take houses one at a time, we have to have a normal distribution for the normal distribution calculator to work. All right, guys, final question here. And I'm going to pop this up full screen. The final question is, what's the difference between x bar, mu sub x bar, and mu? This is a question that almost always finds its way on my final exam. Well, guys, x bar is the sample mean. Mu sub x bar is the mean of the distribution of sample means. And mu is the population mean. That's kind of like, what if I ask you, what's Sx? Well, that's the sample standard deviation. What's sigma sub x bar? Well, that's the standard deviation of the distribution of sample means. And we call that the standard error. And what's sigma? It's the population standard deviation. Now, what's some other terminology we've run into? What's p hat? That's the sample proportion. What's mu sub p hat? That's the mean of the distribution of sample proportions p hat. What's sigma sub p hat? That's the standard error, or the standard deviation of the distribution of sample proportions. And what's p? That's the population proportion. Guys, you all should know this like the back of your hand. There should be no question about what these represent. These are parameters because they express measures from a population. These are called statistics. They express measures from, they represent measures from a sample. Gang, it's all I've got. I hope this helped. Hang in there. Take care.